Hello everyone, welcome to our NS3 tutorial. Today we're going to be talking about NS3. Hopefully we'll get you started with it, and it'll be helpful for your assignment that is due in about 8 days, if I'm not wrong. April 22nd it should be. So let's get started. What is Network Simulator 3? So NS stands for Network Simulator. I realize this is not a very creative name, but it actually is very descriptive. It's a discrete event network simulator for internet systems targeted primarily for research and educational use. So what does discrete event network simulator mean? It actually creates a list of events that takes place in the network and puts a timestamp on each event. And when the time, the virtual time that this simulator is keeping track of comes to the point where this timestamp of a particular event is, that event is performed. Generally, this means every event actually is a call to a function in the simulator, so that when the time comes, that function is called. So in this sense, it is a little bit different from the emulator that we were using, Mininet, because we are not actually creating an actual network and then exchanging actual packets. We are just pretending this is the case with some classes or functions, variables, etc. We're going to be seeing how this is all done in a bit. It's an open source project actively supported by the University of Washington NS3 consortium. NS3 is actually really big. Almost all the network researchers that are publishing papers in literature or conducting some research for their commercial activities are generally testing their system on NS3. So knowing about NS3 will actually help you a lot in your future networking career. Couple of advantages to that. It's an inexpensive solution. It's open source, very easy to set up on your machine to assess network protocol performance, easy monitoring of all sorts of details, such as CWIN. But this is really important because you might recall in the Mininet assignment, in order to be able to measure CWIN, what you needed to do was, because CWIN was a private member variable for the TCP socket that was used by the kernel host, we weren't able to directly look at it. What we needed to do was we created a kernel module called TCP probe that collected some logs, and then we needed to parse those logs to understand what CWIN was. But in NS3, we don't need to do that. Since everything is under control, we have access to all the code that is running this simulation. We are able to set some trace sources, the word that's being used in NS3 is trace sources that will keep track of the different variables at different layers of the networking stack, so that it'll be very easy for us. And of course, we can create custom topologies, especially with large-scale networks. Mininet was bottlenecked by the hardware resources or the CPU resources of the machine that is running the emulation. But in NS3, we can define as many hosts as we like. It'll just be slow because it'll be lots of events to process for the simulator, but it will run. And while it is running, it will not be affected by the underlying hardware resources. So it'll run as if it is a real network with all those hosts and links. And in fact, in literature, you can see that many papers actually, when they are proposing a new algorithm, new method, new system, they generally test this system on a large-scale NS3 simulation with hundreds of hosts, and then in order to show that this is not a simulation-only design, they will implement the system on a very small testbed, generally around tens of nodes, to show that it actually works on real hardware as well. But this large-scale experiment will be very important to convince their readers. That's also good news for you. So for your reproduction project, you can, if you like to use NS3, if you're happy to use it, it'll be very easy to find some experiments that are run in papers on NS3. So you will basically reproduce it if you choose to do so. So there are some couple of disadvantages. One is that you cannot parallelize NS3, unfortunately, at least with the default source code. This means no matter how large your network is, the simulator program will use only one core on your machine. This means as your network gets larger and larger, it'll be very slow to run the simulation. Depending on the size of the simulation, I even had some simulations taking around 10 days, but they were very large simulations. So I don't expect any of you to have that long simulations. Of course, since this is a discrete event simulator, it's running code in an environment where not all the details of a real network are implemented, such as processing delays. What I'm referring to is, for example, in a real switch, when a packet is received, before this packet is forwarded to another port, there's this processing delay. It takes on the order of hundreds of nanoseconds to process that packet. But in NS3, you will see that a switch forwards the packet as soon as it gets it, receives it. So there will be zero processing delay. So you should always watch out for such details that are not implemented in NS3 and whether they would break your assumptions or break the setup that you really want to test. Just a thing to keep in mind.
Can I ask a quick question about something?
Yes, please.
When you said earlier, you said uses virtual time to simulate events. Could you just explain more what that means? And is that just connected to when you said that only it's nothing can be parallelized? Is this used to sort of simulate how an actual network with multiple switches and all would be doing stuff in parallel?
Sure. So virtual time is sort of another time that the simulator keeps track of, and this time only proceeds into the future when all the events that are scheduled for the current time are completed. This means, let's say I am simulating a network with 3 hosts, and they all want to send a packet at time t equals 0 seconds. Okay. By the way, the virtual time starts on 0 in the beginning, and it counts towards future. So let's say 3 hosts want to send a packet to some destination at time equals 0. That means those 3 hosts will schedule an event which calls, say, send packet function. All those 3 events are scheduled for t equals 0. So at time t equals 0, the simulator will run those 3 events or run those 3 calls to the function, send packet, one by one in order. Once all those 3 functions are run and completed, it'll look at the list of events that are scheduled for future. Say the next event is scheduled for t equals 1, then it'll just set the current time to be t equals 1. So it doesn't need to, do anything in between t equals 0 to t equals 1. So it'll just directly skip to t equals 1. And what does completing an event mean? For example, probably a send packet function would just simply create a packet, put it on a link, and then schedule new events that say link can start propagating this packet kind of command for future. And then they would return. Those functions would return with new events scheduled that are appended into this event list. And of course, the event list is always ordered according to the times of the events, so that the earliest event will be always on the head of the list. And sometimes, of course, actually running the code for the event might take longer time than the virtual time. So the simulation will follow the virtual time. That's why I was referring to some simulations being slow. Does that answer your question?
Yeah, that's great. Thank you.
Sure. So this slide, I think, in my opinion, is the most important slide of today's tutorial. I should stress this for a couple of seconds. And the reason is NS3 is NS3 has a very large code base. It's almost impossible for a person to know about every single class, every single interaction, every single module. So what you do, you always refer to this API documentation. So if you go to this link on the left, you will see the page on the right. And basically, on the top right corner, you'll see a search bar. You'll write the name of the module that you're looking for, or you'll write the name of the class that you're looking for. It'll show you some lists that match the string that you're searching for. You'll click on it, and then you'll see all the functions, variables, trace sources, everything related to that class or module. This is actually really, really important for you to be able to complete your assignment as well. So I strongly suggest you to start practicing searching stuff on this documentation. And here on this link, you can also, there are some links to the source code as well. So, if you're interested in how things really work for a particular class module, you can directly see the source code there as well. Okay, so let's talk a little bit about how to build NS3. Basically, NS3 is so the original NS3 is maintained on a GitLab repository, but here, as you can see, I have provided a GitHub link. This GitHub link is for our class's organization, but actually it's a clone of the original NS3 repository. So, in the future, if you want to work on other NS3 projects, just feel free to find the original NS3 repository and then clone it. Or you can continue to use our class's repository as well. Once you clone it, you basically need to run this configuration script. So this buff is actually a script provided by the NS3 developers that handles all sorts of compilation configurations. So we are going to be using this script a lot, actually. So first of all, when you clone it, what you do is you run this buff script with a configure parameter. And of course, while configuring, you can set the build profile. Let's set it to debug because it allows us to do lots of printing. And then we're going to also enable examples and tests just for the sake of being able to see those. But let's say in the future you have developed your own system and then you want to test it, and obviously you want your simulations to be optimized for performance. You want them to run fast. You want them to complete sooner. Then you wouldn't enable examples and tests, and you wouldn't use the build profile debug, but you would use build profile. I think it's called optimized. And once this configuration is done, you will run WAF, and this WAF will actually compile all the source code for you. This will take some time. You will also do this in your VMs as well. I am expecting your VM to take around 4 to 5 minutes to compile. If you're trying to work on NS3 on your own computer or some other place, this time might change, but I don't think it should take much longer. And once the compilation finishes, you can test whether all the NS3 functionalities are working. And for that, you can run the test.py script on the root directory of this simulator. But it takes a long time. So just make sure you have that time, because when I tried it on this class VM, I think it ran about half an hour or more. And the good news is you don't really need to run it for the sake of our class assignment. So in order to test whether everything was compiled correctly, I would suggest you to run this Hello Simulator program. What it does is it's an empty simulation script that just prints out hello on the terminal, and that's it. And if it does run and if it does print out what's expected, that means you're good to go. So of course, today the tutorial I'm going to be going through is going to be a very brief one, just to get you started. If you guys are interested in learning more about NS3, here I have a tutorial link that has been written by the actual developers of the simulator. It's pretty detailed, and it's very good enough to get you started on writing your own systems, own simulations. So yeah, if you're going to work on NS3 for your own reproduction project, I suggest taking a look at this link. Let's talk about running some scripts with arguments. So in NS3, what you do is you create your own C++, I don't want to say program, I want to say script, because it's a very simple C++ file that you're going to be creating. And that file will have reference to all other NS3 primitives. And with those references, it'll set up the topology, it'll set up the workload, it'll tell what to do with this network to NS3. And then you will run that C++ file, C++ script. And in order to run it, what you need to do is, again, using this WAF script. By the way, can you guys see my cursor? Cool. So WAF has this parameter run. And when you call this, you will give the name of your program. For example, in the last slide, we were using the Hello Simulator. This is actually a file called hellosimulator.cc, but we are not giving the extension. So we would write the name of the program itself. And then if that program accepts some arguments, we would give those as well. In our case, in this NS3 assignment, we don't have any arguments. So I'm just giving them here for information. And if you want, NS3, of course, sometimes comes across some bugs, and sometimes programs just exit, and in order to be able to debug it, you can use GDB with it. And here you see the syntax that you would use to run the same simulation program or script with GDB. And once you run this command template, it opens up the GDB screen for you, and then you can use the regular GDB commands, run, next, skip, breakpoints, etc. WAF also has this CWD, change working directory command, that will allow you to set different directories as the working directory. If you don't set this, the default is the root directory of the NS3 repo. And for the sake of our assignment, you don't really need to use this parameter argument as well, just for your information. Okay, let's start with the key NS3 abstractions.
Sorry, can I ask another quick question?
Sure.
The syntax for the debugging, is the %s there, the like format string parameter, is that just for the args, or would we need that if we're running a program that doesn't have any argument?
I think you wouldn't need the args part of that, but you would have the %s symbol, which would actually insert the program's name into this GDB command. Okay, so as I said, the way NS3 works is that it has its own abstractions to let you define some network, some workload, and then some events. And then at the very end, you'll just click on run. I mean, you wouldn't click, you would just write simulation run. You would call this function, and it would start handling the events in order. The most basic abstraction in NS3 is a node. So node is a basic computing device, an host, you can think of it as like, or you can, so switches are also defined from nodes. Any computing device in your network would be node. And then you would add, application protocol stacks or peripheral cards to make it work. How? Let's see that. So between nodes, you should create channels. For example, in this assignment, we'll be using point-to-point channel. Point-to-point meaning there will only be 2 nodes that are connected to this channel. You can think of this as like a cable, because in real life there are some channels that have multiple hosts connected to it. For example, Wi-Fi. You can have lots of laptop, your TV, your mobile phone, all connected to the same Wi-Fi channel to talk to your router and connect to internet. But in our case, we're going to be working with point-to-point channels. Here you are seeing this point-to-point helper class. This is, so in NS3, we have lots of helper classes that will allow you to create channels, install them on some other, stuff. In channels case, we need to install them on nodes. This helper class will help us to do that. And for that, basically, again, you'll write point-to-point helper to the documentation search bar. It'll give you all the functions related to this class, which will include install, create, set, get, etc. Okay, so creating a channel itself is not enough. We need to install it on the nodes, and when you install it, it gives you some net devices. So again, net device is the name of the class that actually represents the network interface cards on our computers, NICs. And those net devices handle layer 2 networking. All right, so once we have the net devices, is this complete? No, we will need to, in every host, we have a networking stack that includes the TCP/IP code that also has some other modules as well, such as in Linux, you can find a traffic controller, TC, if you have configured it before. You can find some other, for example, UDP as well, ICMP, ARP. They're all included in this internet stack. So in NS3, that is the internet stack helper class that handles this. We will basically, again, create an internet stack and install it on a node. Of course, is this enough? No. One last thing, we need to create some applications that actually create and send packets or receive them so that we can create some communication. This is just like what's going on in our computers. So there are some applications. For example, in Mininet assignment, you used iPerf. iPerf is an application that creates some packets which are sent through some TCP/IP layer into the node channel received by the other side. So in NS3, we need to create our own application as well. Differently from Mininet, we are not going to have the same applications as we had in Mininet, because Mininet was using the applications that are already on the Linux kernel, iPerf, ping, fetch, or curl command. But in NS3, there are more custom applications. We're going to be looking at them. So you now have the understanding of how to create a network in NS3, and that's actually all you need to understand what's going on. But of course, if you want to get more detailed into using NS3 to test your own systems, own designs, there are some links that I leave here. Feel free to check them out, that they will help you about how to create your own model or own module. So I will talk about what modules are in NS3 in the next slide. But let's talk about what does creating my own model means. For example, TCP is a model of a layer for communication, right? Instead, you can do UDP, or you can design your own protocol or own congestion control protocol, whichever you like, and then write the code for it, add those files to the source code, and then in your simulation script, just call those new modules or new models to test their functionality. So those links will help you do that. And in case you get stuck throughout the quarter, feel free to reach out. I'm happy to talk about your NS3 environments. And the last link here is the way of logging. As I said earlier, logging is one of the greatest benefits of NS3 because seeing everything, ability to seeing every single detail on this networking stack is something we sometimes need to make sure that everything is working perfectly. So for more detailed information about logging, feel free to check this link out. Okay, now I would like to do some starter code overview. Let me share my screen once again. Oh,
just a quick question. Should we look at those links for this project, or is that more for if we're for like the final project?
Yeah, more for final project, but yeah, feel free to check them out before the assignment as well. So let's take a look at the starter code. Here we are in the GitHub repo of our starter code. You're going to be cloning this repo. Make sure that when you clone, it also clones it as a. So first of all, we strongly suggest you to have your own repo so that you can keep track of your own changes. This means you can fork this repo first to your GitHub account and then clone it from there so that you can push your changes to that fork. But when you fork it, since this is a public repo at the moment, your fork will also be public. Make sure to change that to private before pushing any changes. Otherwise, you risk violating the honor code. Anyway, so this is the starter code of NS3. Here you are seeing the WAF script, for example, that I have mentioned before. You don't really need to, read the content of it actually. Maybe more importantly, again, as we did have in the, here it is. In the Mininet assignment, we have a run.sh script. This is very similar to what we had in the Mininet assignment. It sets some parameters for your simulations, and then it has a to-do here. This is important. This was not to be filled in the Mininet assignment, but here you will need it. And then it runs the actual simulation script. And then afterwards, it runs the Python script that plots the figures for you. So for this plot bufferbloat figures.py, you don't need to fill in anything. It'll create the figures for you if you have collected the correct data. And once everything is ready, it starts a simple HTTP server so that you can see your results on your browser, as you just did in Mininet assignment. Okay, so after going through this run.sh script, let's take a look at the actual code that you need to fill in. So NS3 has its own directory called Scratch. This is a directory that this WAF script I mentioned takes a look at when compiling the source code. So if you want to create new simulations, you would create the simulation script inside this directory so that they would be automatically included in your source code. They would be compiled accordingly. So in Scratch, you have the plot bufferbloat figures.py, which I mentioned, that plots the figures figures for you. Plus, you have the bufferbloat.cc file. This is the file that you want to fill in. So let's take a look at it. So unfortunately, I'm not able to go over every single detail in this script, but I strongly suggest you to read it in detail and try to understand what every single piece of code is doing, as it would be very helpful for your future projects as well. So let me start from the main function first. This main function is, as you can understand from the name, is the main piece of code that creates the network and runs it. But in addition to those, we have some helper functions that are defined on the top. Those functions are actually used for processing the trace sources. So I mentioned about those trace sources, right? For example, cwind. The way TCP is implemented in NS3 allows you to trace cwind. But in order to trace it, what you do is you set up a callback saying, hey, whenever this trace source cwind changes, call this function that I created here, and that function will do whatever we want to do with it. For example, in this case, it will write it to our log files so that once the simulation is complete, our plot figure script can just read those log files and then create the figures for us. So we have a cwind tracer. We have Q occupancy tracer, so we can also trace the Q occupancy. And we have RTT tracer. Those are all the three variables that we were tracing in the Mininet assignment as well. So we will do the same here. let's go through the main function. Again, we start with some variables about the topology, but as I mentioned earlier, you can always provide arguments to your program. So we have the same arguments we had with the mininet assignment: the bandwidth of the host, bandwidth of the client, the delay, the link delay, propagation delay, or the total amount of time we want to run the simulation for, or the maximum queue occupancy, or the buffer size in the network. In addition, I have also added the transport protocol that you want to run with. So by default, you all need to run it with TCP Neutrino, and you don't need any other protocol. But I think it would be really fun to test other protocols and see whether they actually mitigate the buffer bloat, or how do they really behave. And these are the list of protocols that you can try. All right, so let's continue. Here, for example, I am declaring the log files or the trace files in NS3 language.tr that will keep all the information about the trace sources, the C-wind, RTT, and Q occupancy. I'm declaring those files, and those files will be used later. I start with creating nodes as well again. So as I follow the slides, you were able to see that I was building from nodes to channel, net device, internet stack, and the application. I will follow the same order here, actually. I will start with creating nodes. So for to-dos, you will see that fill in here signs. These are the pieces of code that you need to fill in. So let me give you a hint on this at this point. Since now we know that nodes has this type of node container, you know what to look for in the documentation to find this function that should be filled in here. And after nodes, we create the channels. As I mentioned earlier, point-to-point helper is the class that we're going to be using to create channels. Before actually creating them, I actually tell this helper to about the properties of the link or the channel I want to create, such as the data rate, delay, or the buffer size. So here you will see that drop tail queue, the buffer size is set to 1 packet. And the reason for that is we are going to be setting our own artificial bottleneck buffer. So that's why we don't use the drop tail queue on this link. And then after the channel configuration, we create the devices, as I mentioned in the slides. Again, we have some to-dos here. And then what's next after the net devices? The internet stack, right? I will start with the internet stack, but before setting the internet stack, I should set some defaults, such as the TCP segment size, or the buffer sizes, some acknowledgement variations. If you have worked on Linux before, actually, the way networking stack is modeled in NS3 is very, very similar to Linux. And then once the defaults are ready, I will install the internet stack, which is a very basic function, install all. So here is the point where I create this artificial bottleneck buffer I mentioned, which is basically a queue disk. And then we are going to be setting its size accordingly. And then once the default queue size is set, we will install it on some net devices. All right. Once everything is the internet stack is installed, of course, we need to give some IP addresses to those nodes, right? We need to configure them. So this is what I am doing to give everybody some IP addresses. And once everybody has some IP addresses, NS3 has this very cool function, populate routing tables, which will populate all the routing tables automatically so that you don't need to do it manually.
Can I ask a question about the setting IP addresses part?
Sure.
Why do we set an IP address for each node?
I lost you for a second. Can you repeat the question?
Yeah, so like on line 277, you assign an IP address for 2 net devices, the H1SO net devices.
Mm-hmm.
Instead of assigning IP addresses for H1, then SO, then H2. Why is that necessary?
Yes, so let me try to annotate on the screen if I can. Yes, I can. So in our topology, we have a switch in the middle, and we have an N host. This is going to be H1, connected to the switch, and then switch is connected to the second N host, H2, right?
Right.
In networking, here we have a different network, and here we have a different network. That's why we are assigning IP addresses twice in this code here.
Right.
And this set base will actually create a /24 network, assign this network to this first link, and then it'll ask for a new network, which will create another /24 network, and it is installed onto the second link. That's the basic idea.
That makes sense.
Okay, so let's continue. Now we have the routing tables set, IP addresses configured, everything is working. We need to start setting the applications. In this assignment, we are going to be using an application that is very similar to iPerf, meaning it'll create a long-lived flow. And this application, for that application, of course, we need to set some IP addresses or some addresses that this application will use as the receiver. So the sender should know about the address of the receiver, obviously. This is what we are doing here. And then we will create the receiver app, and this receiver app will be, where is it? A packet sync helper. So this packet sync helper is another type of application that we use on the receivers, which will basically accept some packets. That's it. It will not send any packets. It will not do anything. It'll just accept some packets. That's why we are using it as the receiver. But for the sender, we are using bulk sender helper. This is an application created to send start long-lived flows, to send lots of data. Here we are configuring it, and again, after we set some defaults for that application, we need to install it on somewhere. Where you need to check that out from the documentation. Here, once everything is set up, I would like to tell the simulator, tell NS3 that I want to keep track of the event of a TCP connection, but since the simulation has not started yet, I cannot, because the TCP connection doesn't exist at the moment. That's why I schedule an event. This is why it's called schedule. I schedule an event that will be triggered at this time, trace start time. And at this time of the virtual time, it'll call the trace cwin function with some arguments that are required for that function. This is how you schedule an event, actually. I also do the same for RTT tracing. So now, here is the most important part of the NS3 simulation. Up until now, we didn't start the simulation. We need to tell the NS3 that everything is ready, start running now, start looking at the event list. This is the part that we do it. For that, you need to check out the simulator class in NS3. So that's all for our starter code. Once you fill out all the to-dos here, you should be able to create your figures and then answer the questions that are asked in the handout. So let me go back to presentation mode again.
Really quick question. You said that you were going to talk about what a module is and what it means to create your own module.
You're right. I'm sorry. I forgot that. Let me go back to the starter code back. Okay. So this is the root directory of our simulator. In this source directory, you'll see a list of other directories. All of those are different modules in NS3. So by the names, you can actually guess what they are doing. Generally, the most frequently used module is the internet module. And if you enter into that, there is different directories that have different types of files, but mainly the model directory is the one that has all the source code for every class or functionality. For example, ARP handling is part of the internet module, and ARP itself is a model. So you can create your own model, or you can create your own module. Basically, if you are just going to add a simple algorithm, or if you're just going to add simple functionality, you would create a model and add it into one of the existing modules. But for more complex projects, such as if you're going to invent a whole new way of networking, then creating a new module would make more sense for you. So that's basically it. And whenever you add a new file, new model file into a module, this VS script, V script is the WAF script actually, has the list of all the source files. So if you're creating a new file, you would just need to add it to here so that it is compiled along with the rest of the source code. That's basically it. Let me present. So this is the last slide I have. The grading rubric. It is very similar to the mini-net assignment. You will, so 3 points for producing working code that generates graphs, but if some parameters are missing or some functions are empty, you would lose some points. 5 points for answering the questions, 1 point for each. The questions are listed in the handout. You should write your answers on your own README file that will be located in the outputs folder. More detailed instructions are on the handout. And then 1 point for producing correct graphs. So one of the advantage or disadvantage of a simulator is that for figures, you will see that it is not as dynamic as the emulator. And in fact, you will need to elaborate more on that. why it is this case, etc. And one point for design and code quality. So this point we have is to make sure that, you know, when you're writing a code, this class is about reproducing research, right? So we need to make sure that your code is readable, reproducible, and it teaches something to other people. So for this point, your README file should also be clear, clean. It should have clear instructions on how to reproduce what you have done. And it should have clear documentation on, you know, what to look for, what is where, etc. So this is all I have. Good luck. The due date is April 22nd by midnight. But I would strongly suggest you to not leave it until the last couple of days. Utilize our office hours and Piazza. So that's it. Do you have any questions?
I do have a question about the format of the config for the trace functions. So I noticed that in the list of trace sources, congestion window is one of like the bullet pointed things in like the green NS3 classes in the documentation. And I wasn't sure when we were writing our own if we should be tracing like the NS3 : class that contains RTT, or just tracing like the specific variable like congestion window seems to do. So I guess what I'm wondering is like which green class is congestion window in trace congestion window? I can show you the.
What do you mean by the green class?
Yeah, like this NS3, so like congestion window occurs in here and in here. And then RTT occurs in one of these other ones. And I was wondering like, what is this object?
Yes, so those objects are different classes that have the trace sources listed there. The class that you're using actually is in the starter code. So if you look at the starter code, you'll see which classes are being referred to. So then you will have the option of looking at that class only.
Thank you so much.
Sure. Any other questions? Going once, going twice. All right.